Right, so I'll give you a brief outline of what we have seen so far, right? So, yeah, so so far we have seen in ELE 301, right? ELE 301 was our first subject, right? So, yeah, we have seen about AC theory, right? And then we have seen about circuit theories, right? DC circuit theories, right? And yeah, and then we have seen about diodes, right? Right. So as I said earlier, you will have 4 questions in the end of course exam for this unit. So one each, and then we have transistors and FETs left, right? So out of these two, you will have one question, right? So one each. So 4 questions you have to answer 3 out of 4, right? So we have done tutorial on these 3 sections. This is left. So once you come back to the university, I will cover this section, right? We are given 2 weeks of direct teaching. So we can do some practice question along with the last section, right? Transistor section. It's easy to have direct classes, right? Rather than online classes. Right now, we can go to ELE 302 G3, right? The structure also same, right? You are going to have 4 questions in your end of course exams with 2 in-course assessments, right? So you have to answer 3 of them, and you will have a practical session as well, right? So far we have done about 4 practicals, four online practicals, and once you come back, we can do another 8 or 10 practicals, right? Altogether, that's enough for both courses, and then we can have a practical exam as well, right? So that will be done once you come back to the university, right? In this section, we are going to see about integrated circuit, right? ICs, right? Integrated circuits, and then we are going to see about operational amplifiers, right? Operational amplifiers. We have done one practical in this one, right? So hope all of you are aware of how you can use operational amplifiers to design simple electronic circuits, right? So we will see about how we can use operational amplifiers theoretically in today's class, right? The next section is digital electronics. Right, in digital electronics, we have 2 sections. One is sequential logic, one is combinational, right, and the other one is sequential, right? Sequential circuits, right? Combinational electronics and sequential electronics. Finally, we'll have what? An introduction to microcontrollers, right? I'll give you a brief introduction to microcontroller circuits and how we can use microcontrollers to design simple circuits. So how we can apply how we can use microcontrollers to solve our day-to-day problems, right? So here also you are going to have maybe one question from this one question from combinational, and one question from sequential, and then one question will be from microcontrollers and IC together, right? So that's all about the course structure, right? So today we are going to see about this one, right? The ELE 302 G3 chapter, right? So these three are, you are clear about it, and we have done tutorials and others as well, right? So 1, 2, 3 is done. So this is left. This will be done once you come back for your direct classes, right? Now we can start ELE 302 G3, which is the subject for your second semester, right? So we can start with operational amplifiers, right? Which is one of the easiest and simple subject, right? Operational amplifier. right? Operational amplifiers. Oh, IC741, right? IC741 integrated circuit number, right? This is the circuit number, right? The IC741, right? So yeah, I'll mm, yes. Right, I will upload the lecture notes in Google Classroom or in your I think I have sent it to you to WhatsApp, right? I send you the lecture notes in WhatsApp, is it? Okay, I will upload it in Google Classroom as well, right? I will upload it in Google Classroom as well, right? So don't worry about it. So yes. So we can see about operational amplifiers, right? An amplifier, right? The term amplifier is a kind of a device, right? I can say it as a device or a circuit, right? It's a circuit which amplify the magnitude of the signal only, right? It cannot do anything with the frequency of the signal. For example, you have an amplifier with a gain of A and you have an input and you will have definitely an output, right? So this is called as a two-port network, right? One is your input port, the other one is your output port. So this is called as a two-port network. And then here you may have your I in, which is input current, and then across these two you will have your V in, which is input voltage, right? You have your V in and I in, input current and input voltage. Similarly, you will have I out, which is your output current, and then you will have V out as well, which is the voltage across the terminals, right? Output voltage, right? So I in is input current, I out is output current, V in is input voltage, and V out is output voltage, right? So we define the gain, right? So we define the gain A equals output divided by input, right? It just gives you how many times the input signal is multiplied, right? For example, if it is a current gain, sorry, voltage gain, we mark it as AB, right? Then that becomes V out divided by V in. For example, if V out is 1 voltage and V in is 10 millivoltage, what will be your gain? 1 voltage is 1000 millivolt by 10 millivolt. So your voltage gain will be 100, right? The voltage gain will be 100. Since both are voltages, V out, so voltages, this voltage gain is dimensionless. It's a constant, right? It's a constant. Similarly, we can have it as current gain, AI. This could be your I out divided by I in. Output current divided by input current. For example, if your output current is 1 ampere and input current is 10 milliamperes, then you will have the gain, which is current gain, as 100 as well. Again, we have both I and I up and down, right? Denominator and numerator. So this 100 is also dimensionless, which is a constant, right? Which is a numerical constant. So AV and AI both are numerical constant and they don't have any dimensions, right? They don't have any dimensions. Suppose if we have V out divided by I in, right? V out by I in. You have an amplifier which has input current and then output as voltage. Then you will write your gain as V out by I in, right? So in this case, we can write it as, we know that V equals I into R, right? Using Ohm's law, V equals I into R. So I can write R equals V by I. Am I right? V by I. R equals V by I. So since this is V by I, the dimension of your gain will be the dimension of R. Am I right? The dimension of your gain will be dimension of R. Right? So here we call it as trans resistance amplifier. Right? Trans resistance amplifier. Right? This is called as trans resistance. If your output is current and input is voltage, then that becomes, using Ohm's law, right, I by V. So I can make it as 1 over R equals I by P. Am I right? So the dimension of these gain will be 1 over R, which is conductance, right? R is resistance, 1 over R is conductance, right? So we can write it as AGO, trans conductance. This is trans resistance, this is trans conductance, right? The dimension of trans resistance will be the dimension of ohm, right? So the unit will be ohm, and the unit for transconductance will be mho, O-M-H-O, right? This is O-H-M. Mho will be simply the other way around, right? M-H-O. The unit for resistance is ohm and unit for conductance is mho, right? M-H-O. Ohm, we are just simply writing the other way around, reverse, right? In a reverse order, M-H-O. This will be, or the symbol will be the upside down ohm sign, right? So this is trans conductance. So we have 4 different types of amplifiers, and now we'll see about operational amplifiers. Oh, sorry, I forgot to mention that. So in these simple amplifiers, I can say that V out is directly proportional to V in. Am I right? V out is directly proportional to V in. I can simply write it as V out is equal to AV into V in, where just I am cross multiplying this one, right? So V out equals AV into V in, and this proportionality constant becomes your voltage gain. Right? Voltage gain, and that depends on what you are using, or the the output what you are getting from the amplifier and the output you are giving to the amplifier, right? Okay. So now we'll see about operational amplifiers. An operational amplifier, all of you have studied in your A levels, right? An operational amplifier is a simple differential amplifier. I'll draw the circuit diagram of the operational amplifier. So we have minus, plus, output, right? And then we will have supply. This is plus VCC minus VEE, right? And then this will be my V out, right? This is my V minus V plus, right? This V minus is called as inverting terminal. Right? This is called as inverting terminal, and then V plus is called as non-inverting terminal, right? Right? This is inverting terminal and this is non-inverting terminal, right? And then we have output voltage. In an operational amplifier, right, if it is working under open loop conditions, right, there are no feedbacks, right, there are no connections between plus V out to V minus or V out to V plus, then I can write it as V out is proportional to V plus minus V minus, right? So actually the voltage V out is directly proportional to the voltage difference applied between these 2 points. Clear? The voltage difference between voltage difference applied between inverting and non-inverting terminal, right? Always the non-inverting voltage minus inverting voltage, right? So we can write it as V out equals to AO into V plus minus V minus, where this AO comes open loop gain, right? This AO becomes open loop gain, right? Open loop gain, right? So we have these, as I said, it's a simple differential amplifier. So your V out is directly proportional to V plus minus V minus, and then we have the proportionality constant, which is open loop gain, right? Now let's see how the internal circuit of the operational amplifier is, right? So as I said earlier, as we seen earlier, if you have an amplifier, it must have an input resistance, output resistance, and gain. Okay, before going into that, I have plus VCC and minus VEE. What is the reason of these two voltages? Actually, these are the two voltages or two power supplies given to the operational amplifier. So your V out cannot exceed V plus VCC or cannot go beyond minus VEE, right? So under theoretical conditions, the maximum voltage at V out will be VCC, minimum voltage will be VEE, right? It cannot go beyond that values, right? Now let's see how the inside. Okay, I'll draw the operational amplifier circuit with the internal resistance and output resistance and all, right? So okay, I'll draw it a bit bigger. Right, so this is my V minus, and then this is my V plus, right? This is inverting terminal, this is, sorry, yeah, this is inverting and non-inverting terminal, this is my V out, right? Of course, I have power supplies, I'm just leaving it now. In between these two, I will have an input resistance, which is Z in, right? This is Z in, right? This resistance is Z in, and then across V out I have Z out, and then this is AO, right? I have a current source which is AO, this is grounded, and this one will be Z out, right? So this is the kind of a circuit which is shown inside of a operational amplifier, right? So now just tell me, what is the current from minus terminal to plus terminal, right? It is actually, right? So let's take okay, I1, right? I1 which is going inside the operational amplifier. So I can write I1 equal to, right? So this one minus this one, right? So V minus minus V plus divided by that in, right? So there will be a very small current, right? Practically the Z in will be much higher, right? The practically Z in will be much higher. Similarly, when you connect a resistance here, when you connect a resistance here, you have the current voltage, right? Sorry, the A into V in, right? This is your voltage gain, which is comes from, oh sorry, V, I would say plus minus V minus, right? AO into V plus minus V minus, this one, right? So whenever you apply a ZL, right? So resistance, right? This will be ZL, which is a load resistance, in this voltage, a small part of the resistance will be dropped across this one, right? So these two will become a potential divider and part of the voltage will be dropped across the output resistance, right? So your V out, which is the voltage across ZL, is always depends on the value of ZL, right? The voltage is depends on, or it V out will change along with the ZL, right? So with these conditions, solving circuits will be bit difficult, right? Under these conditions, solving the circuits will be bit difficult. So what we are doing is we are assuming a hypothetical device which is called as an ideal operational amplifier. This is a practical operational amplifier, right? Practical op amp. Now we assume that to simplify the circuits only, right? We assume a hypothetical device which is an ideal operational amplifier, right? So we have about 6 or 7 properties of an ideal operational amplifier, right? Ideal op amp, right? As I said here, see, this is the practical operational amplifier, right? For an ideal operational amplifier, your Zin must be infinity, which means that should be open circuited and the whole branch should be removed from here. Am I right? So if I draw the circuit, that will be something like this, right? So you have V minus and V plus, right? This is inverting terminal and this is non-inverting terminal, and in between this one the resistance is infinity, right? Which becomes the first property, Zin, or the input impedance, is infinity. Hence there are no resistance, right? Then what is the current entering into the operational amplifier? What is I1? Since it is open circuited or the resistance is infinity, right? So your I1 is V minus V plus by Zin. When Zin becomes infinity, I1 becomes 0, right? So for an ideal operational amplifier, the first golden rule is the ideal operational amplifier does not draw any current from the external circuit, right? Since it is internal, input impedance is infinity, there are no current entering into the operational amplifier, right? And also, as I said earlier, you will have a small output impedance as well, and that influences your V out, which depends on the ZL, right? So if you want to make the voltage V out as an independent value, so your Z out should be 0. Clear? Your Z out should be 0, right? So the second property of an operational amplifier is Z out is equal to 0. So that becomes A into V plus minus V minus, right? So, and there are no Zin. The voltage is directly applied to the V out, and that will be applied only across your ZL, right? So the second property. So your V out does not depends on the value of ZL if you have Z out equals 0, right? So these are the two important properties, and also an ideal operational amplifier have a few more properties, right? The first one is the input impedance is 0, right? The second one is the output impedance is input impedance is infinity, output impedance is 0. Again, next we assume that for an operational amplifier, the voltage gain A is also infinity, right? Okay, look at here. In a practical amplifier, we have the AO, open loop gain, which has a finite value. For example, it could be 5,000, 10,000 or 20,000, right? and then this will be my V out. So if I draw the characteristic, right? So transfer characteristic, this could be V plus minus V minus, right? And then this is V out. This is V out. So what I can say is my V out is, if I write it in the mathematical form, V out is equal to AO into V plus minus V minus. Am I right? So your V out is directly proportional. It's actually Y equals M into X. Am I right? This is my X. Right? So Y equals M into X. I will have a straight line through origin, right? I have no C, so I have a straight line which goes through the origin, but I have a limit. As I said earlier, it cannot go beyond VCC and it cannot go beyond minus VEE, right? So if this is VCC, that will be saturated, and if this is VEE minus, then that will be saturated. And this will be the characteristic curve of a practical operational amplifier, right? Suppose if I use an ideal operational amplifier, then my A out becomes infinity. Am I right? AI becomes infinity. As we seen earlier in the ideal diode characteristics, infinity means there will be a sharp increment, right? So if I draw that characteristic curve, that will be something like this, right? That will be something like this, because if it is very small, right, V plus is a bit higher than V minus, it could be plus VCC. If V minus is very much higher than the V plus, then that could be minus VEE. So this will be the curve of an ideal operational amplifier. Do you have any class at 9 o'clock? Hello? Hi, do you have any classes at 9 o'clock? Okay, so we can stop with this and I will continue. I'll put the recording in the in YouTube, right? Or I will share it through, I think, yeah, your data charge will be free. I have told that you can download the videos free of charge if I post it in Moodle, right?